Well, this video is gonna talk about the properties of sound, or some properties of sound, and the first one I want to talk about is the Doppler effect. So the first thing we have to realize is that there is a difference between frequency and pitch. So frequency is simply what's being generated by some source, like an ambulance or a fire truck or a siren of any sort, and the pitch is what you actually hear. So depending on your motion with respect to this source, you're going to hear different things. Okay? This has nothing to do with loudness. Loudness is a different story, because as you get closer, you hear something louder. But in addition to that, as you get closer, you hear a different pitch, whether higher or lower. We'll talk about that in a minute. Now I'm going to explain the Doppler effect. So there's a picture in there, but I'm going to actually talk about it here. So let's just say I have a source here that generates sound in all directions. Okay? And up there and down here. So let's say I have an observer here, one, and I have an observer here, two. And let's just assume that this source is moving in this direction. And let's just say that for now that these observers are stationary, they're not moving. So if you notice, as the source is making these waves, it's also going in the direction of the waves. So you can see that these crests, these waves, will be closer to each other, which means the wavelength, okay, will be shorter, okay, which results in a frequency being higher. So that's why if a fire truck is coming closer to you, in addition to hearing it being loud, you hear a different pitch. In this case, we hear a higher pitch because the frequency went up. But the truck or this source is still generating the same frequency, but what you hear is just higher than what's being generated. For this person here, the waves are generated, but the source is running away. So these waves here, or these wavelengths, get longer. In other words, the space here is going to be greater, which means the frequency will be less. Okay, and that's the Doppler effect. Okay, so the Doppler effect is the frequency that you hear, depending on the relative motion of the source with respect to the observer. Okay, now I have a formula here, and you can read the formula later, but I'm going to try to explain different cases about that formula. So let me just try that. I'm going to actually minimize this. That. Minimize this. Okay. Just open up the page. Okay, that's better. All right, so I have a bunch of cases that I would like to try. So the first one, okay, and I'm going to go back to the formula. So the formula basically says frequency equals of FO. Basically, this is what you hear. Sometimes we say F prime. This is the frequency of the source. Okay. And as I do these examples, I'm going to keep changing. Now, there is a plus and minus, or a minus and a plus here, something like that. Okay, so we're going to try to see when to put the plus and when to put the minus. Now, FO is what you hear, that's your pitch. Fs is the frequency of the source, that's what's being generated. V is the speed of sound in the medium. So in this case here, we're going to pretty much do the speed of sound in air. VO is the speed of the observer, and Vs is the speed of the source. So I have a bunch of examples I would like to do here. So let's just say, do maybe 3 or 4 if I can squeeze 3 or 4 here. All right. So I'm going to put, this is the observer, the source here, stationary. With this one, I'm just going to here I'm going to do stationary source here. The observer is going away. The observer is going closer. Now I'm going to do the observer is stationary. Okay, and I'm going to have maybe like an ambulance. That's the source coming towards them, and then I'm going to do stationary observer and source, which probably is an ambulance going away from them. So let's look at these cases here. So in the first case, I have to decide, am I going to hear a higher pitch or a lower pitch? So let's see what we can do. Now, the source has a velocity of 0. So basically for this one, it's going to be Fs. Actually, you know what? I'm just going to worry about this part here. So it's going to be V, V, VO, VS, V, VO, VVS, VVO, VS. And we have to decide on the sign. Right. So the source here is not moving, so this is gone. Source here is not moving, that's gone. The observer here is not moving in both of these cases, so that's gone. Okay. So now let's make a decision. Now, if the observer is moving towards the source, we should expect a higher pitch, okay, because they're getting closer. So in other words, the waves are coming more frequently. So I think this should be a plus here. Okay. If the observer is going away from the source, so as these waves are generated, okay, he's running away from them, so we should expect a lower frequency. So the only way we get that is we subtract here. You have to know your fractions. So by making the top bigger here, right, you made this whole fraction bigger than 1. By making the top smaller here, you made this whole fraction smaller than 1, which means what you hear is going to be less than what's being generated based on this equation here. Now, in here, the source is coming towards the observer, so we should expect a higher pitch. So now, in order to do that, now, what do I have to do here? Plus or minus? Well, if I put a plus, I'm going to make this smaller than 1, which means I expect a lower frequency. That's not what should happen. I should expect a bigger frequency. So the only way that will work is putting a minus there, and then you end up with a fraction bigger than 1. So let's look at this case. The source is going away from the stationary observer, so this observer should hear a lower pitch. So if I put a minus here, this will be greater than 1, so I should be putting a plus to expect something less than 1, and so that FO is less than FS. So you have to just look at your fractions. All right, so I have other cases I would like to try. The other cases is, I'm going to try to squeeze all of them in here. So let's say this is an observer. I'm just going to say the source is maybe like a fire truck or an ambulance. So here is the source. Let's just say they both going in the same direction. The next case is the source is here and the observer is going away, but still in the same direction. The next case so I did that. So I'm going to make them come at each other. So I'm going to turn this the other way around. And the last case, probably guessed it. So I'm going to make the source and the observer go away from each other. Okay. In opposite directions. Alright, so let's see. So in this case, okay, so I have to put back. So I have to put back the velocity of the observer. Okay. And the source here. And the source here. Okay. Now we're going to do this one thing at the top by itself and the bottom by itself. Okay. Now, if the observer is getting closer to the source, okay, we should expect a higher pitch. So we should add up here. Okay. Now, if the source is going away from the observer, okay, we should hear a lower pitch. So I hope you understand the fractions here. So if the source is running away from the observer, we should hear a lower pitch. So the way to hear a lower pitch, okay, is you have to make the bottom bigger. So you're going to put a plus here. So I hope you can see that. So you do it one at a time. Okay? Now, let's look at this one here. The observer is going away from the source. Okay? Okay, so it's running away from the source. So we should hear a lower pitch. So maybe a minus here. The source is getting closer to the observer. So if the source is getting closer to the observer, we should expect a higher pitch. A higher pitch means you have to make the denominator of the fraction smaller, or as small as possible, right? So what do you do? If you put a plus here, you're going to make the whole thing smaller, but we're expecting a higher pitch because of this motion here. So we should put a minus here. Okay? Okay, so we did that. So let me see the other ones. So this is the observer. Now in this case here, the observer is going towards the source. Okay? So we should hear a higher pitch. So that should be a plus. Okay? Now the source is going towards the observer also. So we should hear a higher pitch. Now to hear a higher pitch, in other words, you want to make this fraction bigger. So what do you do to the bottom? You make it smaller, right? So you subtract so that you get a higher pitch because of this motion of the source towards the observer. Now let's look at the last case. The observer is going away from the source. Okay, so if that's the case, the observer is going away from the source, we should have a minus because that's a lower pitch. Okay? Now, if the source is going away from the observer, we should hear a lower pitch also. So the way to do that, you have to put a plus here. Because in other words, you want to make that, you want to lower that fraction. So what you do, you put a plus at the bottom. So let me just make sure I covered all the cases. We did that, we did that, we did that. Yeah, I think we did all of them. Okay, and we'll do some problems in the class and in part 2 of the video. All right, I'm going to jump to page. I'm going to talk a little bit about resonance, and a lot of this stuff here I can't talk about it. I can't do too much in the video because we have to do some demonstrations. Resonance is when one object, right, that's resonating, okay, will make another object that has the same natural frequency vibrate also. And I'm going to leave that for class, and you're going to see what I mean by that when we do this. We talk about these examples when we do some demonstrations in class. All right, and the last thing I want to talk about is beats, and that's another one that we have to really do a demonstration in order to understand it. So you get beats if you play two notes or two frequencies that are very close to each other, right? So you get this high and lows, right? They're following each other now. If the frequencies are exactly the same, you're not going to hear any beats. But if the frequencies are slightly off, you will hear the beats. If they are way off, here I say 1 to 6, I think you can push it to 10 hertz. If there's a difference from 1 to 10 hertz, you probably can still hear the beats. You hear the highs and lows, but if they are too far apart, you just hear two different frequencies. And that's pretty much what they use to tune musical instruments. So if the instrument is supposed to play a certain note, okay, and the other a musical instrument is supposed to play the same note, they play them together at the same time, and they listen if there are beats or if they are in harmony. If there are beats, they'll have to either tighten some strings or adjust the musical instrument. So a lot of this stuff is just going to be done in class. Now, the only math that you have to do here is the beat frequency is equal to the difference of the frequencies of the two objects. Okay, in absolute value, we're looking at just the positive difference, the magnitude of the difference. All right, and a lot of this stuff will be done in class. And that's it. Another short video.